Okay. So, we will continue our previous lecture, that is the properties of Riemann stages integrals, and in this lecture we will particularly deal with the step functions, and we will show that whenever alpha becomes a step function, alpha is taken as a step function, then Riemann stage integral reduces to either a finite sum or maybe infinite sum of the terms series in the form of the series. So, one can get the value of the integral in the form of the series. Okay. Similarly, if alpha is a differentiable functions, then it can be reduced, Riemann stage integral reduced to a ordinary integral, just a definite integrals, and one can get the value easily for that. Okay. So, prior to this, before starting, we will give the definition of a unit step function. We define the unit step function. The unit step function I is defined by I x is 0 when x is less than equal to 0 and 1 when x is greater than 0. So, basically this is entirely a line. So, I x b means when the x, real number x is less than equal to 0, the corresponding value of I x will be this, and when it is greater than 0, the corresponding value of I x will be 1. This point is not included here, it is included here. Okay. So, this is our step function, we call it as a unit step function. If we as a note, we can say, if suppose I take s be any real number in the some interval say a b, and when we say x minus s, then the meaning of this is 0 if x is less than equal to s, and 1 if x is greater than s. So, this will be starting if s is say positive or maybe negative, or s is negative. Suppose I take s here, then all the real number which are less than or equal to x, the image of under I will be 0, and while it will be 1 when it is greater than this. So, this is the real line. So, this all about the step functions. Now, we will make use of these step functions, and first we will show that if our f is continuous and also alpha is a step function, then in that case the integral can be computed just by computing the value of the function at the point where the function is continuous. So, the result is this. The result says, if suppose s is a number lying between a and b, a b is a given interval, and f is bounded over the closed interval, bounded on the closed and bounded interval a b, f is also continuous, f is continuous on at the point s, which is in R lying between a and b, and suppose alpha x is the unit step function x minus s. Okay, alpha. Then the result says the Riemann stage integral of the function f with respect to alpha from a to b over the interval a b is nothing but the value of the function at a point s where it is continuous. So, that way we can easily get the value of the function Riemann stage integral. If I know this property that alpha is a unit step functions with respect to say s, where alpha x is I x minus h, and f is bounded and continuous function defined over the interval a b. Okay. So, let us see the proof of this. In order to prove this result, let us use the, since f is giving to be a f is continuous and bounded also. So, we can function f over the interval a b will attain its maximum and minimum value, because the interval a b is closed and function is continuous. So, it will attain its maximum and minimum value. Therefore, we can find out the maximum and minimum Riemann sum for this function f. Okay. So, let us consider a partition P having the point, suppose x naught, x 1, x 2, x 3. It may be more point, but just for simplicity I am taken, and the result can be extended when there are so many other points involved in between a b. Okay. Where x naught I am taking as a, which is less than x 1 is suppose s, and less than x 2 which is less than x 3 is suppose b. So, this is the interval a b. We have partitioned this interval by choosing this partition x naught, x 1, x 2, x 1, x 2 and x 3 is b. So, this is our say x 3. Okay. So, let it not be this here, this will be x 2, clear, this will be x 2. So, x 1 is s, this is our point s, we have taken this one. Now, consider this upper sum of the function f with respect to alpha over this partition P. So, this sum is sigma m I delta alpha I is 1 to 3, and that is the meaning of this is m 1 delta alpha 1, m 2 delta alpha 2, m 3 delta alpha 3, and if I further expand it, delta alpha 1 means it is defined over this interval. So, the choosing as alpha x 1 minus alpha x naught, this is our m, then m 2 alpha x 2 minus alpha x 1, then plus m 3 alpha x 3 minus alpha x 2. This is by definition. Now, function, since our alpha x is given to be the I x minus s, is it not? So, this is the value is 0 if x is less than or equal to s, and 1 if x is strictly greater than s. Now, here x 1 is s. So, it means when the value of alpha at the point x 1 will be 0, value of alpha at the point x naught is 0. So, first term will be 0, the second term will be m 2, alpha of x 2, since x 2 is greater than s. So, alpha of x 2 will be 1, and then alpha of x 1, because it by definition it will be 0, and then m 3, alpha x 3 and alpha x 2 will all be 1. So, basically you are getting m 2. So, upper sum will always be m 2. Similarly, we can say the lower sum of the function f with respect to alpha will be the small m 2, like this. Okay. Now, since f is continuous, at s, so it means this is our x naught, x 1 which is s, x 2, x 3 which is b. So, if I take any arbitrary point here, say x, the value of f x in this value is nothing but what? This is always the maximum value of this will be because it's m 2 is the maximum value over this interval. So, it will be the maximum value of this f x will be m 2. Okay. So, it will approach to this. So, function f is continuous s, therefore, limit of the function f x when x tends to s will be f s. Okay. But the function f is such which is defined over this interval x 1 to x 2, the function f x is our alpha x into this. So, when you take the value, the value will be m2 and this will come out to be f of s. So, both m2 will go to f of s and m1 similarly small m2 will also approach to f of s because of the continuity. So, both m2 and small m2 will go to f s and small f s. Small m2 will also go to small f s, and because this is the largest value and smallest value, but as x approaches to s, this will go to f s. So, m2 will approach to f. Similarly, small m2 will approach to f s. So, this shows that both upper sum of the function when the limiting value of the is limit of this x tends to s is our f s, and that is the infimum of this, and which is equal to supremum of the lower sum of f with respect to alpha. So, this shows integral a to b f d alpha will be f s, because always this limiting value is coming to be f s. So, upper sum when you take the infimum value it is f s, when you take the supremum value of the lower sum it is also f s. So, it is integrable and integral comes out to be this. So, this proves the result. The second result also in connection with the step functions, which will give the result that if alpha is a step function, then a Riemann integrable integral stress integral will be reduced to the infinite series or a finite series depending on this. So, suppose C n is greater than equal to 0 for n is equal to 1, 2, 3 and so on, and let sigma C n 1 to infinity is convergent. Let this converges, okay, is convergent. Let this is convergent. The sequence S n is a sequence of distinct point. Let sequence S n be a sequence of distinct points in the interval a b, in the open interval a b, and alpha x is the step function n equal to 1 to infinity. This we call a step function. Alpha x is this as C n I of x minus S n. Let it be number 1, okay, and let f be continuous on the closed interval a b, continuous on the closed interval a b. Then the Riemann stress integral of the function f with respect to alpha over a b is equal to the summation of the series 1 to infinity C n f of S n. So, Riemann integral can be calculated in terms of the series if alpha is given to be a step function. So, that is very important result we get. So, proof of this. Okay. First thing is that since sigma of C n 1 to infinity is convergent and I of x minus S n is 0 if x is less than equal to S n and 1 if x is greater than S n. So, this implies that the series 1 to infinity C n of say I of x minus S n will always be dominated by the series sigma C n 1 to infinity, because this term this will help, this will reduce when all the terms for all x which are less than S n, the terms I of this will be 0. So, the series will have a lesser term and all the positive terms. So, it is less than equal to C n, and but this is given to be convergent. So, this is given. So, by comparison test the series sigma 1 to infinity C n I of x minus S n is convergent. That is the first thing which you get it, and convergent for every x. For every x belongs to the interval say a b. Here of course, we can choose the real line also there suppose for every x. Okay. Now, let us take the alpha. What is alpha? Alpha is given alpha x as sigma n is 1 to infinity C n I of x minus S n. So, what is the value of it? So, if we put x equal to a, x lying belong to a b. So, let it be in the interval a b. Okay. So, x is suppose a, then what will be the alpha a? This is our interval a b, and here these are the S 1, S 2, S n. These are the points where S 1, S 2, S n they belongs to the open interval, remember, because these are the points of distinct. So, say S 1, S 2, S n and so on, these are the points. So, a is strictly less than S 1, a is less than S 2 and so on. So, when a is strictly less than 2 S n for each n, therefore, I of x minus S n will be 0. So, it will be 0. But what is the alpha of b? When you take x of b, all the S n's are less than equal to b, are basically less than b, is it not? So, it will be completely the value of this will be 1. So, what we get from here that alpha a is 0, alpha b is 1 and alpha x is an increasing function, is a monotonically increasing function. That alpha s 1, when you take x equal to x 1, then it is less than x equal to x 2 and so on. So, it is a monotonically increasing function. So, alpha is a monotonic function first thing, and this is okay, and alpha b. Okay. So, what is sorry, this I of x n is 1. So, basically 1 into sigma, here I am sorry, this will be I of you can write this thing as sigma C n 1 to infinity, and this will be 1. So, you are getting sigma C n, sorry, this is 1. Okay, we are getting this one. So, one thing is clear that this will be a monotonic increasing function. Now, let epsilon l greater than 0 be given. Okay. The series, since the series sigma C n 1 to infinity converges. So, the remainder term of the series is less than, so we can choose. So, for given epsilon l greater than 0, there exists an n such that the sum of this series n plus 1 to infinity C n will remain less than epsilon l. Let it be, because by definition of the converge, the remainder term of the series is convergent. So, this is less than epsilon l. Okay. Now, this will be let us put alpha 1 x be the sum of this series of first n terms C n I of x minus S n, and alpha 2 x I am taking the sum of this series where the terms are taken from n plus 1 onward of the series C n I of x minus S n. Let it be this 2. Now, since I of x minus n, because of this becomes a step function. So, sum of the step function, and in case of the step function, previous theorem we have said it is a Riemann integrable functions. Okay. So, the sum of these Riemann integrable functions, we can write the sum of this. Therefore, we can say f is alpha d alpha 1 sorry step function. So, integral f d alpha becomes the by the if alpha is a step function, then integral f alpha x is nothing but the f s, is it not, that what we have seen. So, here, so we get from there is, so this implies the integral a to b f d alpha 1 is nothing but the sigma I is equal to 1 to n I is equal to 1 to n C n n is equal to 1 to n equal to 1 to n C n f of S n. Okay. So, this will be alpha 1 and this is number 1, because it will follow from the previous result. This result is there which we have proved earlier. The result is this, is it not? According to this, alpha is giving to be continuous, f is continuous and this one. So, already f is continuous given and bounded and alpha x is this. So, value will be this f s. So, here if you take this sum, if you take the integral of this f of alpha 1 x and dx, then we get immediately this can be written as the sigma into this form. So, there is nothing to explain. Now, further, what is our alpha 2 b minus alpha 2 a? What is alpha 2? The alpha 2 is defined as this. This is alpha 2 x. So, if I replace x by a, then alpha 2 a x will be 0 and alpha 2 b will be sigma of C n. So, basically this is equal to the sigma n plus 1 to infinity C n, but which is giving to be less than epsilon because of the series is convergent. So, remainder will be less than epsilon. Hence, therefore, the integral a to b f d alpha 2 with respect to alpha 2, the modulus of this is less than or equal to a to b mod of f d alpha 2, is it not, d alpha 2 or mod of d alpha 2, and then d alpha 2 again this is bounded. So, it is less than or equal to m times and m times integral a to b d alpha 2 mod of this and mod of this, and this value is nothing but the alpha 2 b minus alpha a, which is less than epsilon. So, this is less than m into epsilon. Okay. So, let it be the equation 2. So, over alpha 1 we are getting this thing, over alpha 2 we are getting this thing. So, where m is the supremum value of the function f x over the interval a b. Okay. That is what. Now, since our alpha is nothing but the alpha 1 plus alpha 2, because when you take the alpha x is the sum of this series 1 to infinity. I break up into two parts, 1 to n and 2 n plus 1. So, alpha is alpha 1 plus alpha 2 x. So, we get from here is then, so integral a to b f d alpha minus sigma I is equal to 1 to n is equal to 1 to n and then C n f of S n mod of this. Now, this will be, this can be written as what? It is nothing but the mod integral a to b f d alpha 1 minus sigma n is 1 to n C n f of S n plus integral a to b f d alpha 2, because this d alpha is alpha 1 plus alpha 2, we can write this. Now, this part is already giving to be less than epsilon, this part is less than basically this entire thing alpha 1 is the same as this. So, this part is 0, we get this cancel, only this part is left and this part we have shown this is less than m into epsilon. So, it is less than or equal to m into epsilon, but epsilon is arbitrary. So, when as n tends to infinity, epsilon will go to 0. So, epsilon will go to 0, therefore, we get integral a to b f d alpha is nothing but the sigma n is 1 to infinity C n f of S n, and that is complete the results. Okay? That's the result. So, this one clear. So, what this result says is that in case of the function alpha is a monotonically is a step function, then our Riemann stress series integral reduces to a infinite series or finite